So that's the generic notion of dissipativity, with special cases to passivity, non-expansivity, and static systems. So now we go further and simplify this concept to something called quadratic supply rates. And we will take even a simpler model for the system where you know, this particular system has this form x dot equals f plus gu, and we call such a function as affine function. It becomes linear when f is 0, but in u, but the correct term in this particular case is affine. And also the output is going to be affine. Instead of h of x comma u, more complicated function, we will call that as this h plus j times u and affine in u, right? So then we define this notion of quadratic supply rate. So G is dissipative with respect to a quadratic supply rate R if R happens to be a quadratic form of U and Y, okay, and specifically with respect to some these matrices Q, symmetric matrices Q, and then some arbitrary rectangular matrix S depending on the dimensions of U and U and Y. And we, for short form, instead of calling it dissipative with respect to quadratic supply rate, R of U is equal to Y transpose QY and plus 2Y transpose SU plus U transpose U. I mean, it's going to be mouthful. So instead, we will call it as QSR dissipativity. And it's probably a coincidence that QRS happens to be continuous in this English alphabet, and QSR is the same acronym as quadratic supply rate, right? So when we say QSR's dissipativity, it's quadratic supply rate, but with matrices Q, S, and R in that order, where Q and R are the terms, square terms, so to speak, and then the S is the cross term. So anyway, and as usual, we will look at this differentiable storage function. If it happens to be differentiable, then basically we can see that this part vs prime times f plus gu coming from the x dot part is less than or equal to this supply rate expression. Okay, let us pay attention to this particular expression. You have this first part v times f, that is in some sense independent of anything, right? Rather independent of u, and the second part is linear in u, right? And then the last part is quadratic in u. The other two parts seem to be constants with respect to u, and then linear with u, but actually y itself is h plus ju, so you can actually substitute and you will get quadratic terms out of both of these things, but also linear terms and also terms that are independent of u. So essentially, after all said and done, this inequality is actually a quadratic inequality in the variable u. And what does that mean? Well, perhaps I should spend a moment in this and then actually go back to, I'll probably write something. So what we have here is V F plus GU is less than or equal to Y transpose QU Y plus 2Y transpose SU plus U transpose RU, right? So Y is H plus JU. So Y transpose QY is, if I expand, and H transpose QH plus 2 times H transpose QJU plus U transpose J transpose QJU, and then 2Y transpose SU is going to be simply 2H transpose SU plus 2U, that's U transpose J transpose SU plus U transpose S transpose JU. Okay. Yeah, so that's about it. Yeah, so all said and done, basically we'll have some quadratic expression. Okay, I'm going to write it as quadratic expression in U, And what is true about that? I mean, if let's say I'm going to bring everything into one side, right? So less than 0. Okay. For sake of simplicity, basically, I'm going to say something like, I don't know, pick something. So some gamma of x comma u is less than equal to 0, whereas gamma is actually quadratic in u. It's not arbitrary. So it could be nonlinear in u, but x, but it could be arbitrarily nonlinear in x, but it's quadratic in q. So if you have a quadratic in u and it happens to be consistently less than 0 for all x and u, okay, one of the conclusions that we can draw is perhaps there is a square function of a linear function u that when you add that you will get 0. Or in other words, basically what I'm saying is this is kind of equivalent to some kind of linear function. Sorry, this is u in u, and multiply with it itself, so you get a quadratic in u, and that will be equal to 0, right? So this is what we are going to use, where gamma is coming from all this complicated expression. And when we expand, what happens is basically, you have a constant part, let's say gamma 1 of x. This may look something like gamma 2 of x times u plus u transpose gamma 3 of x u, and plus all this is equal to 0. So it will be obvious that basically the gamma 1 plus L transpose L is going to be 0, and gamma 2 plus perhaps L transpose W is going to be 0, half of it, I don't know, and plus gamma 3 plus W transpose W is going to be 0, right? So out of this quadratic expression, whenever we see a quadratic expression and equate all three powers, the constant and the linear part and the quadratic part, you get three expressions and three equations, so to speak, right? So if we do all that for our problem, what gives us is basically this very complex looking equations: v prime of x times f minus h transpose qh plus L transpose L is equal to 0, and so on and so forth. And if you are a keen observer of what has been going on, these are nothing but Kalman-Yakubovich-Popov conditions, but in the nonlinear sense, right? But of course it's more generalized. The original KYP lemma was discovered for linear systems that satisfy positive real condition, and if you recall the definition of positive real, actually it's essentially the same thing as passivity. So the original KYP conditions for linear systems were there for passive systems, and these are for nonlinear dissipativity with respect to some quadratic supply rate QSR, right? So that's why we call them as extended KYP conditions, and much of this theory was actually very well presented by a couple of authors, Hill and Moylan, fantastic papers, a little bit after the original papers by Willems. Though some of the references that we have in this particular course do deal with these concepts quite in detail, the original paper by Willems and then followed by Hill and Moylan are still very good papers to read, in my opinion. So anyway, it's not a surprise that all the versions of passivity and non-expansivity are a special case of quadratic supply rates. What I mean by that is basically when Willems was probably putting everything together, he wanted to ensure that this quadratic supply rate is kind of defined so that at least it will cover some of the standard cases, and then eventually hoping for these kinds of KYP conditions. If you specialize these particular notions to passivity or the positive real lemma that we spoke about earlier, and these equations will become boiled down to simply what we see in front of us, nothing more interesting than just a special case, but good to know that these are the nonlinear versions of the positive real lemma we had earlier. So if you recall the positive real lemma, the way we stated is in terms of a linear matrix inequality, whereas here we present it as set of three equations. Both are one and the same. You can write this in fact expression in terms of a nonlinear matrix inequality. But in the case of linear matrix inequality, you have a method of checking for that through your LMI toolbox or something like that. In the nonlinear case, it's not so obvious. But still, if you further specialized these systems to say polynomial systems and things like that, then we can use the semi-definite programming or sum of squares toolbox to actually solve this particular problem as inequality, right? So keep that in mind. So this set of three equations is actually equal to one nonlinear matrix inequality, and for special case of polynomial systems, we can use things like SOS toolboxes to check. So if we actually take the non-expansivity definition where gamma is equal to 1, then you will get the nonlinear version of the bounded real lemma, which essentially is what we see here. Like I said, there's nothing interesting beyond the fact that these are the most important notions of dissipativity, but also generalizations of very standard concepts, right? Now, one of the most interesting things that we have to note is in the case of systems with no input, we saw how the derivative of f of x, the Jacobian matrix we called, if that happens to be Hurwitz, then we can conclude that the nonlinear system is stable and things like that. So we have a similar concept in dissipative systems. The specific results one can refer to the book by Haddad and Chalaboyne. But basically, if we actually pick this A to be the Jacobian, B to be g of 0, C to be the derivative of the output function, and D is j of 0, then what is not surprising at all is basically if the original nonlinear system is QSR dissipative, then with a differentiable storage function, then we can guarantee that there exists a non-negative definite P, unlike the standard expressions where we are guaranteed to have P, right, positive definite. Here we can only guarantee P greater than or equal to 0 such that this inequality is satisfied. So I apologize for the typo. This should be less than or equal to 0. Okay, so this inequality will be satisfied, right? Why is this P non-negative definite? Well, again, many times, if v of x, let's say in the standard case of Lyapunov function, v of x happens to be x power 4, that's much smaller than quadratic, but nevertheless it's a non-negative definite function and things like that. So in such cases, the linearization will produce 0 as your Lyapunov function. Okay, so and anyway, there's something beyond that. If somehow we can show that AC and is observable. If you recall, we considered observability concept way back when we were looking at some of the linear system concepts. Essentially, this observability matrix CA square and so on and so forth, if that has full rank, then we say that AC is observable. If that happens to be the case, then we can guarantee that P is going to be positive definite, right? Now this is same thing as looking at your g of s given by this transfer function. Will satisfy this bounded real lemma, generalized positive real lemma. So kind of an expression on all real part of s greater than is 0, right? So we have seen this concept in a different context from a linear systems perspective, robustness, but they're all special cases of dissipativity. And specifically what we are trying to say is, if there is a nonlinear system that is dissipative with respect to a quadratic supply rate, then we will actually get a corresponding linear system which happens to be generalized positive real. Okay, so what we have seen so far is basically we defined dissipativity through the concept of a storage function. If there is a storage function, we developed all these results. Now in reality, suppose somehow we know that this is a mechanical system, the obvious thing is basically to conclude that it's going to be passive, right? Typically through this force velocity pairs or current voltage and things like that. But in general, it could be passive with dissipative with respect to some other supply rate, and then we are at a loss in terms of how we can arrive at a storage function, right? And then this question was considered by the inventors of this dissipativity theory, and the answer seems to be quite interesting. Just like the converse theorem for Lyapunov functions, which said basically if you have an asymptotically stable system, we can actually construct the Lyapunov function through some magic, through this k-class functions and things like that, quite a complex kind of functions. The conclusion is basically we have a Lyapunov function if we have a system that is stable, right? So here the definition of dissipativity itself is directly in terms of quote-unquote Lyapunov function, or specifically the terminology we use as storage function, right? So can we actually define dissipativity without ever talking about the storage function? The answer is yes, and then it turns out quite interesting, and then there's equivalency between many of these concepts, right? So Willems basically therefore defined this concept called dissipativity with respect to supply rate without ever talking about storage function. The only difference is basically this inequality that we see here, integral t 0 to t of r of u comma y should be non-negative for all time. But the solution is going to start with a zero initial condition. So we have to, in some sense, intuitively, if you start with zero energy, what will happen to this particular system? Basically, all the external supply is going to be kind of accumulated into the system, and then that's going to be greater than or equal to zero is what it's saying, right? So beyond the understanding of the physical implications of this, take it as a mathematical definition. Basically, you start off the system at zero initial condition and look for this output for a given input, and if r of u comma y happens to be non-negative for all time, then we call that as a system. And again, as usual, these definitions are so complicated, right? What do we do with this? It's these kinds of definitions. We can't do really much, and then that's where the KYP conditions come into picture. But for the KYP conditions to come into picture, we need a storage function. So next couple of slides we will discuss that. So anyway, if this inequality is satisfied as equality with further condition that the final state is also zero, it's starting at zero, it's probably coming back to zero with an input, then we call that system as conservative, or specifically the term we use with respect to this abstract systems as lossless with respect to the supply rate, right? And then there is a exponential weighted version which is quite useful in many scenarios. Okay, so therefore the question that now comes because is basically, for this particular kind of system, if we know that there is a system which I can somehow magically prove that this integral inequality is true for all values of u and y and t greater than or equal to 0, it's obviously humanly impossible to do that unless you have very simple expression for the solution of this particular system. Somehow magically that that particular thing is true. Is that the same thing as saying that it's dissipative with respect to a storage function vis a vis? And the answer obviously is going to be yes, and this notion of available storage is defined, right? Available storage is this complicated looking infimum or a supremum, and so here basically we start the initial condition at x0, and let's look at this expression once again, and then basically try to understand the definition, right? Available storage is that you start the system with an initial condition and some input u, right? And we are trying to find the function at x0, right? And you consider all kinds of u, and for each and every one of those inputs you will get an output, and compute this integral of the supply rate, right? So keep doing this for various u's and then different times and things like that, and take smallest of those, infimum of all those, or put a negative and then take the maximum. Either is fine, right? They're one and the same. So that will be independent of u or t, because you're trying to get rid of all that by maximizing that problem or minimizing that particular problem. You'll end up with simply a function of x0, and that we call as available storage. Now this available storage is going to be non-negative, and I put a question why, and give it a second to think about. if you actually pay attention to this expression, basically we'll have supremum of some bunch of numbers there, and that number, when I pick t equals capital T is equal to 0, it's essentially that integral is going to be 0. So it's all bunch of numbers where 0 is one of them, right? So we're trying to take maximum of those things. So maximum is certainly going to be 0 or more. So that's why v of x, va of x0 is greater than or equal to 0. So this, we may have bunch of negative numbers in that integral coming from that integral, but 0 is certainly there. So supremum is going to be non-negative, right? So that's a nice thing to know. I mean, you have this available storage happens to be non-negative. So one of the conditions. This VA being non-negative is one of the properties of storage function. That's not the only thing, right? And again, anyway, we can define the corresponding exponential storage for the case where we have the dissipative with respect to this weighted concept, right? So before we move on and actually convince ourselves, I'm not going to really convince you that this available storage is indeed a storage function, but it becomes important for us to understand a couple of these concepts. So let's say we have a system G, then we call it completely reachable if somewhere in the past some 0 you can reach the current initial condition, or you can take a look at it basically as I'm starting at 0 and then reach some x0. So that is completely reachable, right? And we have another concept which is called completely null controllable, where we start from an initial condition x0 and then reach 0, right, in a finite amount of time. So the difference between these two is kind of reverse. You can come to any initial condition from the origin, that is complete reachability, and you can come to the origin from any initial condition, that's null controllability. Now in the case of linear systems, all these concepts collapse to simple concept of controllability, whereas in nonlinear systems, unfortunately, things get really complicated. And for example, in the case of linear systems, if we just observe y, the output y, and we can pretty much estimate the overall state. Whereas when it comes to nonlinear systems, it's you can define something like that, but it's not necessarily true in a very simple and straightforward manner. So we have specialist concepts, like basically if somehow we know that y is 0 and in the case where u is 0 and then x happens to be 0, that's saying somehow we can guarantee that if y is observed to be 0, then x is definitely going to be 0. It's like by observing y we can conclude something about x, and that's observability. Controllability is through u you can actually control the system. In the linear case, basically the concepts are much simpler. Observability, you can observe anything about x through y if it is observable system, and then you can control from any point to any point if it is a controllable system. Whereas in nonlinear systems, you have this 0 to somewhere and somewhere to 0, and then just observing 0 and things like that. So anyway, this is something that to keep in mind over the next several lectures, that we will be using once in a while some of these concepts, right? So now we're going to connect the dissipativity, available storage, and then another concept that we haven't really looked at. So I'm going to define something called required supply rate. So this is kind of the analog to the available storage. If you remember, available storage, we actually started off from an initial condition, and through the input we go somewhere and then take all those numbers and then take infimum and things like that, right? Whereas required supply rate is basically you start somewhere and then come to x0, right? Come to x0 and then basically compute this R of u's, and that's the required supply. And then it's a physical interpretation. Available storage is I am at a particular initial condition, how much energy I can extract. Whereas required supply, I am at the origin to come to basically a particular state with probably some energy level, so to speak. So what is the amount of energy that's required? So that's why it's called required supply or required energy supply. So what's nice thing about all these concepts is, if G is dissipative with respect to R of u comma y without ever talking about storage function, if and only if these two things, VA and VR, are finite, and they are going to be storage functions, right? So storage functions means it satisfies the standard storage function inequality that we presented in the first couple of slides, right? So not only that, every storage function that may exist beyond these two storage functions will be in the middle in terms of the inequality. So they'll all be finite and non-negative, but every storage function will be greater than equal to available storage and less than equal to required supply. And then this is kind of theory at its best. It's showing that you can do all those things, but this is like the converse Lyapunov function. Nobody is ever going to be able to compute beyond some very simple systems the available storage and required supply. In practice, basically, we hope we could find a storage function just like that, and then through semi-definite programming, as I mentioned, and things like that. So, but otherwise, the biggest problem with any of these things is actually finding that V functions, whether we call it as a Lyapunov function or storage function. The problem remains. But it's good to know that you have these definitions without storage function, but we can actually guarantee existence of some storage functions. And of course, if they are further differentiable and things like that, then we can do much more than that. And then they have their inequalities. Like I said, we can put that as a semi-definite programming problem, things like that. So anyway, the summary of this particular lecture is like this. We know that Lyapunov functions provided mathematical extension to energy, but they were very useful in proving stability of systems with no input. They have stability of equilibria and things like that, right? So dissipation is kind of a natural extension to that concept with inputs, okay, and outputs, of course, but with inputs, okay. So in that sense, the motivation for any of these concepts, when Lyapunov developed this concept, or Willems kind of summarized, basically it always dependent on mechanical systems or systems with energy and power and things like that, defined very well, right? So lossless systems are nothing but conservative systems where energy does not get lost or dissipative, and then this typically exists only at a very small scale, free of all friction and things like that. They don't usually exist, but they do exist, at least theoretically, right? So dissipative systems ensure that the energy may be dissipated but never created. So dissipative systems, mathematically speaking, also they are a special class of systems where this abstract energy cannot be created but only dissipated, perhaps, right? And that's a big special class, and then we basically will show that such a special class of systems have special property like stability, right? Using feedback concepts, we will show that if dissipative systems have certain supply rates, then we can show that the feedback interconnection of dissipative systems will be invariably stable, right? So therefore, this is the what you call, just like stable systems out of all the systems available, dissipative systems are those special systems out of all the systems possible with inputs. So anyway, storage functions, available storage and required supply, we are sure we understand that they are kind of analogs to energy in physical systems. And needless to say, if you take any mechanical systems, electrical systems, or even more generally any system that has some kind of Lagrangian Hamiltonian, some of you who may be familiar with these concepts will realize that actually there are even abstract Lagrangian systems and Hamiltonian systems. All of them actually satisfy some kind of dissipative property, either passivity or non-expansivity, right? So like I said already, basically passive and non-expansive systems are very interesting to start with. They are stable with input 0, and non-expansivity is actually a generalization of bounded input, bounded output stable systems. So many a time we have this very general concept of quadratic supply rate or supply rate in general, but we end up using more of the concepts of passivity and non-expansivity. But we will see examples where this concept of general supply rate, especially quadratic supply rates, become very powerful in solving some special problems. Hopefully we'll get to see some of those details, but in general, all the stuff that we have done in terms of robust control and sector nonlinearity become a simple special case of this dissipative systems. So with that, we will move on to feedback interconnections, but before that, perhaps we will see few examples of dissipative systems, very simple examples, how we can show, perhaps how to identify storage functions and things like that. In some cases, we just pull those storage functions out of thin air. Okay, thank you.